All right. Good morning, everyone. Welcome to Lecture 9 for COMP1511. Welcome to Week 5. Welcome to those of you in Sydney and surrounding areas. Welcome to our first week of lockdown. So, UNSW went into lockdown a little early, but now everyone from Wollongong from Shell Harbour to Newcastle and out into the Blue Mountains has joined us. All right, what that means is UNSW campus is almost shut down. There are a few essential activities happening there. There's certainly nothing happening on campus for COMP1511, so don't go to campus for COMP1511, and be very sure if you think you need to go to campus for another course, make sure that they've very explicitly told you, because almost all teaching is online at UNSW. All right, and of course, you're locked down unless you're outside the sort of greater Sydney area, you've got to stay home. Please stay safe. Please don't try and, you're all young and healthy, but please try not to spread the disease. All right, we're all got fingers crossed that we'll be out of lockdown, and on-campus activities will be resuming after Flexibility Week in Week 7. Flexibility Week is for undergraduates. There's no compulsory activities, no teaching. We will try to run some optional classes. We're still trying to figure out what's good. Some of the tutors are saying, oh, maybe they could do something, so we'll put a couple of optional activities online. So monitor your email. We might even use the regular lecture slots. But just to be clear, these don't introduce new material, and they're not compulsory. The other thing we could do is some activities to help you with Assignment 1. So our first big assessment, Assignment 1, is running right now. Hopefully you've started. Don't panic if you haven't got very far, but please get started now. The earlier you get started, the easier it is to get help. Ideas take a while to sink in. So yeah, don't plan to spend a big chunk of 12 hours making steady progress for 12 hours. Instead, if you could spread out 12 one-hour blocks in your timetable and try and make progress each time. Come back, think about it, ask your tutor questions, read the forum, check for questions, ask questions in the forum. Yeah, spread out your work on Assignment 1. There's a lot to be learnt there, and it won't come easy. We've changed the Assignment 1 due date a little. It was due on the Friday at the end of Week 6. It's now on the Monday just at the start of Week 7, so it's a couple of days later, but the late penalties got larger, so you absolutely have to get it in on that Monday. So it's the change is not as big as it sounds. What else is happening in the course? We have another weekly test. Our second weekly test is due Thursday, so you haven't done the weekly tests from Week 4 last week. It's due Thursday at 8 p.m. and we'll have another weekly test come out this Thursday. We've got help sessions running. Tom sent his usual comprehensive announcement. You should have a comprehensive announcement from Tom last night, I think. With
it was about 10 p.m.
Yeah, 10 p.m. last night. So that and that goes via the course forum, doesn't it? So if you're not getting that,
yes,
you haven't subscribed to the course forum, which is very important. We might even try and send people a reminder. There might be a few students who haven't set up for that. We might even try and remind those.
I was just thinking, I'll send out that email this morning.
What else is happening in the course? Oh, I should warn you. Yeah, with Assignment 1 back finishing, coming in a few days later, that means there's only a couple of days between it and Assignment 2 being out. So it's all go in this end of the course. But on the plus side, I mean, it's Sydney weather is miserable and you're locked in your house except for the 4 essential reasons for leaving, so it's a good time to be coding. And you'll get a break, and hopefully we'll be at the end of the term, and hopefully we'll be out of lockdown and the weather will be better. All right. Anything else that's happening in the course I should tell students about, Tom?
Nope, I think you've covered everything I mentioned.
All right. So I would say, this course, introductory programming courses, are notoriously challenging. They're not the only first-year courses that are hard, but they're certainly up there among them. and you're right in the middle of it. So we're almost to halfway. So yeah, you'll need to be working hard, and everyone's going to be finding it hard. So hopefully we're all going to get there together. Now today I'm going to recap a few things about pointers, and then we'll introduce characters and strings later. So we've got some more material coming. This is not the pointers are a really hard concept, which we're going to practice a bit more with the assignment, with lab exercises and so on. Characters and strings, not so much. There are a few things I'd like to clarify about them, but they're perhaps not as challenging and as important as pointers. All right, first I guess something that's not important, but I'll recap it anyway. We looked at other bases, and particularly base 16. All right, so you can go through all of COMP1511 and not know anything about base 16, about what we call hexadecimal, and that's fine. But base 16 gets used a lot in computing outside COMP1511, and we see it a little here, so I thought it'd be nice to explain to you how it works. And if you didn't understand that explanation, don't worry. The reason it gets used a lot is it's easy to flip between binary and the very bits, the ones and zeros of a number, and hexadecimal. You can do that in your head. It's so easy. It's hard to do that with decimal. So in computing generally, we often want to think about the actual binary representation of a value, and if we can, it's too verbose to actually write it out or print it out. But hexadecimal is nice and compact, so it's just a nicer notation. But it actually doesn't come up much in COMP1511. The only place we really see it in COMP1511 is when you print out a pointer to look at what a pointer value is when you're debugging. You'll see it there. The other place you'll see it a lot is if you see computers breaking. If you see a piece of software breaking, you'll often get in the error dump, the error message, whatever's appearing on a screen, hexadecimal numbers. So now you know what they are. So all right, so that's something that's not important. Pointers. Oh, let's go code for pointers. I think I'd prefer to work with code. All right, on screen is the wonder of pointers. Here we have a program, and it uses the two absolutely key concepts with pointers. Just let me get my little annotation pen working, hopefully. So I mirror my screen onto a Wacom tablet, which I can write on, hopefully, if I've got the right process running, and highlight tiny little bits of important program like that. And there are the two crucial pointer operations there in this one bit of code. The ampersand, often called address of, gives me a pointer. It gives me a reference or the address of a variable. So on its right hand side will be a regular variable. On its left hand side will be a pointer to that type. So on its right hand side is I, which is an int variable. On its left hand side is P, a variable that can hold a pointer, or an int star, often we say, to an int variable. What does that let me do? That lets me use that value to do anything I can do with I. Once I've got a pointer to I can do with that pointer anything I could do with I. And how I do that is using the second operator there, the asterisk. Yeah, it's a bit sad, but asterisk gets overloaded, gets used for a few things. C only makes use of a few punctuation symbols, so it has to use them for different things, which gets a bit confusing. So asterisk gets used for multiply. It gets used to say, look, I've got a pointer, now I want to talk about the variable it points to. That's what we're doing here. And the third place it gets used, which is sort of related, is when I'm declaring a pointer variable, I put an asterisk to say, no, this is not an int variable, this is something very different. This is a variable that will hold a pointer to an int. But the miracle of all this is I can now if I compile that, what have I called this? I have called it pointers.c, what a boring name, but if I compile it and run it, you'll see I go to print out I here. I put 456 in I. I never assigned anything else to I, but I prints out as 24 because I got a pointer to I, and then I said change whatever variable P points to be 24. P points to, P contains the address of I, so that changed I to be 24. Right. In itself, that looks stupid. What does that get me to do? Why do they bother doing that? I just could have done that with a direct assignment to I. Yeah. True. In this little context, that code doesn't let us do anything wonderful. But let me show you where it does let us do something more useful. So I want to write a function that adds 1 to a variable. Now, again, that's not the most exciting function, but it's sort of a proof of concept. It's a good thing to practice, by the way, if you're trying to do things for the assignment, for example. You're saying, can I write a function to do this? If you test it in your 50, 100, whatever lines of code for assignment, it's sort of hard. There's nothing to stop you writing a separate, different, 5, 10-line program to try out an idea. Can I write a function that does this? Does this work? It's an excellent thing to try. So here I'm trying to see if I've just got the ability to add 1 to a variable. This sort of code doesn't work. I can add 1 to this variable here, but this variable here is a completely separate variable that lives only in this function, and so I can't change a variable over in main using this function. That approach doesn't work. This approach, all right, we'll leave that. This approach does work. I can write a function that, given a pointer to a variable, adds 1 to that variable. So this is why we need pointers. This is why you might want to use them in the assignment. I think you have to use them in the assignment. This is what makes pointers incredibly useful. So I want to add 1 to I. I get a pointer to it. I could have done this without creating a separate variable. It's a little clearer with a separate variable. Create a pointer variable called z, make it point to I, pass that to this function. Notice this function here doesn't change z. That's the big thing. It doesn't change z. It changes whatever z points to. So that's why we want pointers. All right. Now where am I? Increment. Oh, all right. There was another thing we saw. Yes, so much happened in last week's lectures. There's another thing we saw, and this is sort of weird. I've just talked again and again about how variables inside functions are their own separate world. Sadly, yes, is it sad? I don't know. Importantly, that's a better word. Importantly, this doesn't apply to arrays. Passing arrays to functions is different. And here's a tiny little program that demonstrates this. What have I called it? Oh, actually, I think I've already got it compiled. I do already have compiled. Oh, I don't know what that. Oh, all right. Let's run it without that. That's demonstrating that a change to an array in this function affects the array, even though the array is in another function. Why? Yeah, it's actually a complicated reason. The full story of pointers and of arrays and functions is something. There are a lot of C programmers out there programming C professionally who don't really understand it properly. You have to have a good understanding of type systems to really know what's happening. But I can tell you a little bit about here. So it looks like the arrays pass to the function. Working on assignment 1, you can code as though the arrays pass to the function. But what's really happens is actually a pointer to the array is passed to the function. Why would they do that? The problem is arrays can be big. 4 bytes, double 8 bytes. How big can an array be? Array can be 1,000 ints, could be 4,000 bytes, could be 1,000,000 ints, 4 megabytes, could be 1,000,000,000 ints, 4 gigabytes. So arrays can be very, very big, and passing them all into the function could get quite expensive. So instead, a pointer's pass to arrays. Don't worry too much about that, but you do have to. The crucial thing is, you understand that this assignment here can change this array there, and you'll see. Oh, actually, I'm not sure. Yeah, no, we've got lab exercises this week. I think that work with this, and certainly the assignment works with this as well. I'll come back to that. What do I want to do that? What do I want to do with this? I've got a few examples here. All right, I wanted to work through a few examples. I think, yeah, there's a couple of pieces of example code. So I'll clarify that with an example. So I'll work through an example of a couple of possibilities with arrays and functions. What else do I want to? Oh, so the other thing we did in the last lecture, last bit of recap, is we wrote a program. Yeah, it's quite powerful. This. So this program is a lot of the code in this course was my idea, but various bits have now been written by tutors, and some nice bits have been written by Mark Chi, who's lectured the course in the last couple of terms. And this one's his idea, and I really like this program. It shuffles cards. So we've got cards. Yeah, I don't know how much physics some of you have done, but there's a classic sort of intro to a physics lecture or physics explanation where they want to talk about the physics of something in the world, and they say without loss of generality we'll assume there's no friction, no air, no this, no that, we'll assume that cows are spherical or whatever. So they make all these simplifying assumptions and then work through the physics. In computing, we often do something similar. We say without loss of generality we'll assume just that everything is an integer. So we assume our cards are just integers. And it actually doesn't change the coding much to have, a regular deck of playing cards with jack of spades, but we're just assuming cards with integers on them. So we read in our deck of cards. How do we do that? Well, here's our first use of breaking things off into functions to make our program more readable. So I'm coming back. I wouldn't say this is beautiful code. It's lacking comments. It's lacking explanation, but it's got a nice decomposition. So up here in main, we can look at main. Main is just 7 lines long, and that's quite nice. So we can just read what it does and start with main. So we can read top down. It declares an array of cards. This little syntax says initialize the whole array to 0. It's a little weird, but that does it. Not a bad thing to do. Not a bad thing to do at all. So that ensures every element of that array has 0 in it. Yeah, we're already seeing a few people confused, asking questions in the forum, which means there are other students sort of who are working it out themselves maybe, who are forgetting to put a value in an array element and then trying to access that array element, and DCC saying, oh, no, that's an error, I'm stopping. And this is one way to avoid that. It doesn't mean you've got the program you want, but it means every array element now has a defined value, in this case 0. So then we call this function here, which reads in our cards. That's a weird function. We'll go down to it. Well, when I say weird, it's actually a common, but it's a little confusing. So we'll come back to how that function works. Then we have 2 functions, which one shuffle the cards and one prints the cards. And this is a classic C thing that you don't necessarily see in other languages. So this is a really classic C and C-like language thing, where we pass we really only want to pass one thing to shuffle cards and one thing to print cards, which is the cards. But we have to pass two inputs. One is the array containing the cards, and the other is the number saying how many things in the array. And you'll be doing this a lot, including in this week's lab exercises. So we have to, we've got one thing, which is the array, but we have to pass two inputs because we've got to pass through that. Why do they say so? Yeah, read the card, shuffle the cards, print the cards. This is good for if I'm trying to work on this program. So imagine you've got this code and you've come back to it after 6 months, or you've been given this as a job. You know, you've got a summer job, and the manager said, "Oh, look, I want it to do this program to do add feature X, or users have reported bug Y. Can you look at it?" You can start here and think, what do I want to look at? Oh, look, the feature better go in print cards, or the bug must be in shuffle cards, and start down. So let's look at the read cards one. Why did I say it was a little confusing? It does two things really. It puts cards in this array, and it needs to pass back how many cards it put in there, so it returns a value as well. So it does two things. One of its job is to put things in the array, which you can see happening there, and the other is when it's all done, it has to return how many cards it put in there. Oh yeah, there's some checking missing there, isn't there? Yeah, we don't check that scanf works. We could add some checking there as well, couldn't we? Yeah, interesting. I think there's a version linked to the lecture slides that's got more checking in it. But really, I wanted to show you that the two things: pass in an array, which I can change, return a value to say how many things I put in the array. We could have also done that by passing a pointer here, and having read cards change whatever variable was pointed to be n cards. That would be the other way of writing this function. There's print cards. That's sort of nice. And there's shuffle cards, which is really cute. It's got this weird little shuffling function, which you have to execute this in your head to see what it does, I guess. And it has to swap two array elements value, and it does it with pointers. This is a function that, given pointers to one int variable, pointer to another int variable, swaps their values about. So if it's got a pointer to x and a pointer to y, and x contain 1 and y contain 2, then afterwards x will contain 2 and y will contain 1. Beautiful function. Alright, that's recapping that, highlighting a few things. I wanted to look at... Yeah, no, we'll look at this function now. Alright. I'm halfway through writing a program, so I want to show you coding up a function using pointers, and then I'll look at a couple of possibilities with it. So what do I want? Apparently I need to print out the squares, the cubes, and the fourth power of a few numbers. Now, I could do this calculation, but I'm thinking it would be better to do this with a function. So can I write a function to do this? And we can figure it out. Now, I can't return 3 things. A function can only return one thing, so it has to be done with pointers. So we'll make the function return nothing. Alright, what's it going to take? It's going to take double. Its first argument will be, I guess a double, which can be x, and it's going to return. It's got to return 3 values, so we can pass 3 pointers. I'm not sure what good names here. So variables it will set to be x squared, x cubed, and x to the 4th. All right. Yeah, I think that will do the job. And then I can call this here and say powers of E. Oh, where do I get E from? Where do I get E from? So I could put 2.718 something something something. Oh, my memory's not very good. Let me show you a little trick here. C actually comes with a few things hash defined already for you in math.h. And I can go man math.h, I think. Manual entries. Yeah, I'm not even sure we've seen a manual entry. We don't have to get into them too much in COMP1511, but you will be seeing a lot more of them as you go along. Manual entries are one form of documentation of commands and library functions on Unix-like systems, including Linux. So yes, if you have a Mac and you're inside it on the command line, yes, you can get a manual entry in there as well, I believe. Now, manual entries, I should warn you, are famously not really tutorials. They're not typically not for people who've never seen the stuff before. They're more for someone like me who's forgotten something and wants to be reminded of it. So reading them is not so easy often, and you've got to skip over some stuff, and often you can get what you want still, even if you are a beginner programmer. But yeah, they're certainly not designed for first-time programmers. But I can go math.h. I don't think math.h is too bad. Let's look at it. Yeah. Alright, it's telling me some stuff I don't want to know. Yes. Yeah, alright, so this really advanced stuff here. Yeah, you're saying I'm an idiot because I don't understand that. No, this stuff is... I've never actually had cause to really read about this. I know basically about, well, I think vaguely what that does, but it's not really... It's weird and unimportant stuff. So there's lots of weird and unimportant stuff there. But if I scan down, there's things that lots of people use. There's hash defined, a value for E and a value for pi. So if I say hash include math.h, let me get rid of that. I'll get that value for E, and I can say, which was ME. And I can say, do that, do that, do that. So pass pointers to variable S, get a pointer to variable C, passes that as our third input, get a pointer to variable F, passes our fourth input. And our first input will be this hash defined value coming out of math.h. We saw math.h, we've seen math.h before because it also defines square root. It also defines sin, sine, cos, tan, and a pile of other functions, but square root is the one we saw. But in addition to that, it defines constants like, oh, how did that become Q? That should be ME. All right. Oh, no, we should be able to, oh, I seem to have repeated code here. Yeah, we'll have to, but we don't know how, we can't turn it itself into a function until we do the second part of the lecture. We can come back to this and maybe make it all to a function. And here we'll call it, and what is it? 42. Alright. So we're calling our function 42 times. Sorry, our function 3 times to do this. Let's come down here.
Andrew, I think there may be a typo on line 8.
Someone reckons there's a typo on line 8.
The x2 is doubled.
They're right. Thank you for the person in the chat for the typo on line 8. Alright, I'm going to compile that. That may compile. It's not a complete program. Remember, if we think we've got a program that compiles, it's good to compile it and find out if there are errors so we don't keep going when we've got fundamental mistakes. The earlier we can find problems, the earlier we can faster fix them. And my problem here is I'm in the wrong directory. I'm in week 9. Alright. Lecture 9. Oh, that's clever. That's impressive. Alright, so the compiler's giving us warnings. It's saying, here look, Andrew, I don't think you put a value in S, I don't think you put a value in C, and I don't think you put a value in F. Let me give you an important life tip here is, you might read this and say warning and think, you know, that's like the signs the council puts up saying at the beach, saying beware, there are waves at this beach. No. Well, sometimes those warnings are important, but this warning, if you're a beginner programmer, this warning means stop. There's a big mistake in your program. Like 95% of the time. There's like 5% of the time where the compiler's warning you about something that's really not that important. 95% of the time that means huge error in your program. So, and it's right. This, I haven't filled in this function. But that's the only thing wrong. So it's saying, look, yeah, this function doesn't finish up putting values in S, C, and F. So let's do that. So what has it got to do? X squared has got to contain x times x. The variable x cubed, x3.2 has got to be assigned x cubed. Saying, does C have a power operator? Not really. There is a function in the math library that you can use for exponentiation, and it can do things to real power. So you can calculate, you know, pi to the 2.5 or pi to the -3. But there's no integral exponentiation operator you might see in other languages like Python, for example. There. All right. I think I've got my function. I think I've got my beautiful function to print out all of these powers and discover what e squared cubed into the 4th power is, pi squared cubed into the 4th power, and 42 the same. Have I got it all right? Apparently I can't spell. Oh, it's still telling me I've got it because I haven't written my file. Come on. That time. What's happened to my P key? Alright, we'll run it as hours. No way. Look at that. I think that's correct. Looks pretty good. E squared, pi squared. Beautiful program. Alright. So that was using 3 pointers to pass back 3 values from this function. Alright, there's a little forced example. This function's not, well, there's a couple of things weird about this. It's a little forced, but it does the job for us, doesn't it? So that's nice. That's showing you pointers being a way to get 3 things back from the function. Is it the only way? No, it's not the only way. You're thinking, could I write this function another way? Yeah, let's try another way to write it. What's that? Let's write it powers 1. How about this? We know if I pass an array to a function, any changes to the array inside the function affect the array outside the function, because a pointer to the array is passed. So I could just pass a single array with 3 things in it and change it. Come on, keyboard. There we go. So we could change the first element of the array to the square, the second element of the array to the cube, the third element to the 4th power. And then we could, oh, now I'm a little worried. Can I do this? Can I have a function here and a variable of the same name? The answer is you can, but you won't have access to the function in here, and it's probably not a good idea anyway in general, and it's definitely not a good idea when we're taking our first steps with programming. I've said try to use, just until you're really confident, just try to use different variable names everywhere. It'll keep things clearer in your head. So I'll give this a different name to avoid that clash. I'll call it pow. Pow, pow, pow. There we go. 1, 2, 3. Hey. Alright. I'll take that up and call it up here. I'll need a double array of size 3. We'll try it out. Is this a different way of writing this function? Alright, let's try this. Alright, so I've got, it works. So I've got 2 possibilities now. 2 different ways of writing the same function. One uses 3 pointers to 3 double variables and sets them. One passes an array of size 3 and gets them back there. Which is better? So that's actually not a good answer. There are pluses and minuses to both approaches. Generally, if you see a function trying to pass back a few things, that's not good. So sometimes it's necessary, but if it's getting to you're passing in 3 or 4 pointers to pass back things, maybe your program could be better structured. That's actually a really hard thing to, when you first start programming, working out what functions to write. So don't worry if you can't figure that out. So this is just passing in one thing, so it's sort of simpler, but then again, I don't really like this idea of putting the powers in arbitrary spots in the array. Maybe these numbers need to be hash defined. I don't think that's a great function either. I'm not going to do it, but I actually think both of those aren't the best way to solve this code. Probably the best way to write this code would be actually write 3 separate functions. One for square, one for cube, one for 4th power maybe. Or maybe one function that took an argument and said, here's x, calculate it to the power y. So I don't think necessarily either of these are great design, but they're really good. What they're good at is illustrating the mechanics of C. So this shows you the mechanics of passing a pointer to a variable to get a value back in that variable. So this function says, I can do powers, give me a pointer to 3 different variables, and I'll put the square in whatever variable the pointer, the first pointer points to, the cube in whatever variable the second pointer points to, the 4th power to whatever variable the last pointer points to. This function says, oh yeah, I do the same thing, but give me a 3-element array and I'll fill it in with the square, the cube, and the 4th power. So great for showing you the mechanics. As a beautiful design for calculating this, not good. It'd be nice to put this code in a function and call it only once. Well, have it code once and call it 3 times. We can't quite do that yet because here we write out E, here we write out pi, and here we write out 42. Yeah, how are you going to do that? In a function. Alright. We'll see how to do that shortly. Alright. Now. Alright. I've got two more things to show you with arrays. Two more things to revisit, which are topics that are really linked into what we're working on. So, printing out an array, dead easy, right? Yeah, well, hopefully printing an array is starting to seem, hopefully the idea of printing out an array is starting to seem, if not dead easy, I'm just hopefully starting to feel confident with it. We're doing other things with an array, yeah, well that's what this week's lab's really about. What have I done here? I want to play with a function, I want to experiment with a function that prints an array. This is a common thing for us to do, is to set up sort of a little main that sets up some data and calls our function once, just for our initial experiments. We're trying to write a general function, so, but we'll write a main that just tests it once. We then may try calling the function other ways, but just to get things started, we'll put a little main in there. And I think this week's lab exercises are set up like that for a couple of them. And it's certainly how we set up a lot of exam exercises. We'll say, here's a main that calls this function, fill in the function maybe. Or we're actually going to there'll be one call to a function, and you've got to write a function that handles many different inputs, but we'll set it up so you're all ready to go with one input. So I've set up the array with one input here, which is 6 numbers. Oh, there's a weird thing happening here, which I thought I'd show you. We don't do this much in this course, but if you don't put the array size in and you do the initialization thing, C says, oh, okay, there's 6 values there on the right. I guess Andrew wants this array of size 6. 6 ints it'll be. So that's actually the same as saying A6. Why have I done that? Yeah, it's sort of to make a point. So normally we'd put something here that's hash defined. But yeah, alright, so let's put the possibilities here. I also don't have to put the size here. Now if I want to write a print array function, at the moment I'm in an impossible situation. There's no way to do this in C. I've got the array here. C does not have any, oh excuse me for a second. Oh, sorry about that. I should, I guess, have a way of muting when I sneeze. Alright, C
Bless you.
doesn't have a way here of saying, you passed me an array, how big is it? It could, but it doesn't. It just doesn't. And why doesn't it? Because, well, what really happens is a pointer's passed in. Nothing about the length of the array is passed in. So there's just nothing you can put there to write out that array. So we've got a few possibilities here. One is we just write a function that always prints out an array of a certain size. And that's often actually all we need in COMP1511. We'll ask you to write a function that always handles an array of 1,000. The assignment is a 2-dimensional array, but it's always a certain size. And of course it should be hash defined. So we could say size is 6. And it's nice to put the size there so that's clear. But then we've got a function that writes out a fixed size. And you can only call, it only works with an array of that size. But for a lot of things we do, that's fine. Alright, so that's one possibility. That works, that's great. I'll even compile it, and seeing is believing. What was my typing today? Oh, there we go. Thank you, DCC. All right. All right. So good enough for a lot of purposes. Good enough for assignment 1. Assignment 1, you do sort of fascinating things, but it's all with arrays that are always the same size. It's hash defined. But what if I want to write a function that's called from 20 different places in my program to print out arrays, and some of the arrays are size 1,000, some of them are size 6, some of them are size 20. What about if I want to handle different sizes? All right. Next possibility then is to write a function that takes 2 arguments, and one of them is the size of the array, and the best way to write it is like the nicest way to write it like this. Oh, actually, no, to avoid confusion, I'll call this length. That's not a bad idea. We'll call that length. It writes out an array of. Oh, that comment was really misleading, wasn't it? So I give it a second input which says how many elements in the array, and then that's easy enough to fill in. Alright, I've got to change my prototype up here. It's a bit more messy to call, but a bit more powerful. What's the best way to do this? Well, I could do it like that, but that's sort of ugly. That will work. We'll do that like that, and then make the program a bit more attractive. All right, so I'll fix this shortly. But there, I've now got a function. You can put, say, write out this 1,000 element array, this 1,000,000 element array, this 6 element array. I've got 2 inputs. First is the length of the array. Second is the array. Less convenient to call. You've got to supply 2 things. A little less readable. 2 things messing up your code, but much more general. Has the interesting side benefit of, if I just want to print the first 5 things from a 1,000 element array, I can say print array 5 and A, and that's actually okay. But a better way to write this would be to have a hash define there. So we'll write that with a hash define. That's but I can call this array, this function, from other places in my program and do it. So that's strategy 2. So strategy 1, always have the array the same size. That's what we're doing in assignment 1. We'll do that in other places as well. Strategy 2, two inputs. One is the length of the array. We'll do that for some of the lab exercises, and that'll be pretty common. We'll have test questions later and exam questions later that involve something that looks like this. It'll be, here's an array of length n. Tell me the difference between the largest and the smallest, or something like that. Common sort of thing to want to do. Really common thing to want. Really important thing to know how to do. You end up doing that a lot. All right, here's a strategy which we could also use. Third possibility. Third possibility is, I'm just going to get rid of the hash define entirely. I'm going to put in the array a special value. I'm going to use -1. That's in the last array element. So in the last array element, I put a special value. Now I can get by with just passing the array to the function. And my function knows when to stop. It can take any size array, and it knows to stop when it sees an array element that's not the special value. Look at that. Will that work? Version 3, strategy 3. Will that work? Let's find out. Oh, it's saying, Andrew, you haven't. It's saying mismatch. By the way, this is saying mismatch. This is you'll see a lot. The error message perhaps not could be clearer, but it's saying, look, you've got this thing on line 18, you got this thing on line 8. They just don't match. One of them must be wrong. It's also saying, oh, you've got this on line 13, and that doesn't match line 8. Line 8 says 2 inputs, 1 input. And what should it be? It should be int array. There. Good. Beautiful. So my strategy works. Is this a good strategy? In some cases, yeah, we won't use this much in COMP1511, but there are places you'll see it, and we're going to see it used in a slightly different context shortly in the second hour. But it's really flexible, isn't it? I can have any number. Well, what are the problems with this strategy? Why don't I like this strategy? You've got to have a special value that you don't want to use for other things. So I can no longer print out an array. I can no longer print out -1. Is that a problem? Might be. Maybe I'm in a context where I need to print out absolutely any int value. Then I can't have a special value. But if I know my values will always be positive, then I can reserve -1. If I know all my values are going to be non-zero, I could use 0 as the special value. So it depends on whether I have a special value available. That's one problem. What happens if the caller doesn't put the special value in the array? Yeah, that's the second issue. If the caller doesn't do the job and put the special value in the array, this will run off the end of the array. So this function can never be completely safe. It depends on the caller giving them an array that meets the specification. It always has a -1 somewhere in it. That sort of creates a concern in our programming. Does that matter? Not for some programming, maybe for others. So if we were doing really code that had to be really rock solid, it was the flight control for an aircraft, maybe we'd be worried about this. Maybe we wouldn't coding in C. Yeah, interesting thought. But it's nice to see this strategy 3, which I don't think you get to use. Sorry, I don't think you get to use strategy 3 in this week's labs, but maybe in week 7. But I will show you it in another context shortly. Alright, so that's 3 strategies for handling an array. I've got one more thing I want to show you. Oh, it's a similar sort of setup. Yeah, so we're asked to write a count big function which counts the big positive and the big negative values in the array nums. It doesn't actually say what big is, but I can fill that in. Not a bad idea, by the way, when you're writing code, is if there's something you're thinking, I want to note this, or Alright, so we want a function that goes through an array and counts up how many big values, big positive and big negative values. Up here we've set up a test array. I'm going to call it with a function. So I guess how would we do that? I haven't finished. And we call the function and then print out what the values were. All right. Well, that should be hash define, shouldn't it? Alright, hash define size, I guess, of 7. If I count it right, 3, 4, 5, 6, 7. Yep. Size. Nums. So this could be coded up much prettier, but that's basically what we want to do. We want to try out our count big function, pass it this array we've initialized, and print out what we get back for b and n. Saying I can code this. I reckon I can code this. All right. I know my loop. Int I equals 0 while I less than length. I'm a bit short of time here. I want to give you a break, so I'm coding up a bit quickly. But a good thing to do at this point would be put a printf in here and make sure our loop does what it wants. But I think I've got a loop that executes once for every array index for nums. Alright. And now we can just say if nums I greater than 100, do this. Nums I less than 100. Alright. Yeah, alright. Goes through, adds 1 to the variable where we're storing count of the big negative. If that's less than 0, adds 1 to the variable pointed to by big positive. If it's greater, if the array element's greater than that. Brilliant code. What could go wrong? Nothing could go wrong. Let's try it out. Yes, something does go wrong here. I can see one error at least, but there may be more. Oh. Line 25. Expected semicolon after. I don't understand that at all. Oh, I haven't saved the file apparently. Ah. Expression result unused. Well, that's weird. Alright. So there's something that worries me here, and this actually goes back all the way to, I don't know, 5th class, when you write 6 times 7 plus 3, the times and the plus are fighting over the 7. If you write, you've got operators either side of a value, who wins? Well, you say, yeah, for plus and times, I know who wins. Times wins. You do the times first and then the plus. So 6 times 7, 42 plus 3. It's not 7 plus 3 and then multiply by 6. BODMAS was the thing we were taught. Same situation is actually happening here. We're saying plus plus and asterisk, and they're fighting over big positive. What do we do about it? If in doubt, we go to brackets. Better would be, I think, here for me to not use the plus plus. I actually don't like you using plus plus until you're really confident with it. It's better to write it out like this. There's no ambiguity there and there. So if you're using pointers, don't use plus plus so you really know what you're doing, or use brackets to make it clear what you want. But I prefer that. Alright. So that says get the value of the variable big positive points to, add 1 to it, put it back in that variable. Get the value big negative points to, add 1 to that value, put it back in the variable big negative points to. That's the code I wanted. My program is now amazing. Yes, we will have a break as soon as I figure out how to save my program, compile it, and fix the last bug. Oh, we were doing so well. Well, that's interesting. Yeah. All right. This is an interesting one. Yeah. All right. This is a good one. Yeah. All right. So we've got a runtime error appearing over here when we run our program. DCC said couldn't spot anything when we compiled our program, but that's not uncommon. Some errors can only be picked up when your program actually executes. It's saying uninitialize a variable access. It's saying, look, you're using the value in a variable, but you never put a value in there. And that's happening line 12. It's happening here, Android. DCC saying you never put a value in B or N. It's not quite the truth. DCC is a little confused here. This is sort of a subtle thing with how this works, but this is not actually where the error really happened. There was an error earlier in the program that the tools DCC users couldn't pick up for complex reasons. But let's look at what we know. You might be saying, I think my code's good. Look, down here I put values in whatever big positive and big negative points to, and big positive points to B, and big negative points to N. Yeah, I don't know why that's B. That's worrying me. Let me make that. Oh, no, we'll leave it as B. That's okay. My code's fine. There's another clue here. There's a nice little clue here. If you see a really weird value in a variable, that's often a sign of an uninitialized value. It's actually the bits that happen to be in that memory beforehand. So that if the variable, the bytes that a variable gets stored in might have been used for something beforehand, and often it looks very different. I'm guessing that those bytes just happen to be used for a pointer, an address. Probably. Who knows? But weird value in B, weird value in N, and DCC saying, oh look, you never initialized them. And it's true. I use the value of whatever big positive points to here. I use the value of what big negative points to there. But I never initialize these variables. And the problem's probably down here. We're counting these things, so we probably should initialize this variable to 0 and this. And that will get me a working program. All right, we're going to take a 5-minute break now, but anything you've got in the chat or whatever, I'll get Tom to give me a summary and things we can talk about. But let's take we've gone well past the hour, sorry, but so let's take a 5-minute break now. Get up, stretch, go to the window, look at the rain falling outside if you're in Sydney or whatever. But a 5-minute break and we'll come back and I'll answer any questions about this code, and then we'll move on to characters and strings.
Sure.
Okay.
All right, everyone, welcome back. Okay. Okay. Someone in the chat, thank you very much, pointed out a huge bug in my program. That should be -100. Tom's said, oh, I don't know about some of the variable names you've been using, Andrew. I think 115 style would complain about these. And I think he's right, and I think it should complain. So 11511 style, it's not a perfect program. And ask in the forum if you think it might be telling you the wrong thing. It's a really hard program to write, and it's done quite a clever way. And it's trying to give you all the easy advice about coding, so to help you. So then the tutors can give you the complicated advice. And sometimes it gets it a little wrong, but it's pretty good. So let's try it out on my Count Big program and see how it feels about that. It is complaining. All right, it's good. It's saying, Andrew, look, you've indented everything properly. So you don't have your ZID in the header. Yeah, that's okay. I'm not for this. I don't need that. But it's saying, oh look, I don't like the variable b there. These two variables b and n, they're not descriptive. And I'd say it's right. So I think they should be given better names. So that's a good complaint for 1.1 style. Those are poor names. They should be given descriptive names. You'll notice it's smart enough not to complain about the use of I here. And I don't mind I there used for a loop index. Often sometimes there is a good name for what you're counting through, but if there isn't, I is fine. So it's doing the right thing here. These should be better names. I won't fix them. I will show you another way to write this program. There is a better way perhaps to write this program, which I think it'd be better probably to use a variable inside the function. We'd call these, give these different names. Maybe that. Make this big negative pointer. And just use a local variable here, a regular variable, to count these things. And then only when the function is done, put the values we've counted up into whatever variable's been pointed to. I think that makes for a nicer function. And that's a sort of common pattern to see. Compute, 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 and just before we return, set the result into a couple of variables. So here we'd say big positive, whatever big positive pointer points at, set it to our little local variable where we've counted up how many big positive numbers there are. And similarly, the last one. So that's it. Come on. Oh, it's wrapping in weird and there we go. Ah. So yeah, I thought it was worth showing you that pattern with my poor spelling. Get to the finish and then set the variables that we've been given pointers to whatever values we've calculated. And I like that because it's perhaps a bit more obvious. Yeah, I do like that. All right, let's change topic then. Let's talk characters and strings. All right, so completely new topic. Characters. What's a character? Characters are ways of writing things. So an example of a character would be A, or maybe capital D, or we could write the digit 3, or we could write a plus sign. So ways of writing a symbol. How does that work with coding? Well, I talked about everything has to become an integer. Same thing applies to characters. We need some way of turning any character into an integer. a mapping is what your mathematicians, your maths lecturers will call it, a mapping, saying this character corresponds to number 27. This character corresponds to number 83. There's a classic and still important mapping, or perhaps you might say encoding. It's saying a way of associating with a number with a character. This encoding is ASCII, the American Standard Code for Information Interchange. It specifies, it's really less than 128 characters, but, well, 128 characters, but some of them are special. It specifies numbers for these. So what do these characters include? Little a to little z, big A or capital A, uppercase A to uppercase Z, the digits 0 to 9, and maybe 20-ish punctuation characters. It says, it just gives them a number. It says little a is this number, big A is this number, and so on. An exclamation mark is this number. It also gives numbers to some special non-printing characters like new line and space. It says new line is number 10, space is number 32. Alright, what good is ASCII? Well, there's a few languages, and the characters they use in writing these languages are all in the ones that ASCII gives numbers to. So you can write your English, you have to write English, you can just use ASCII characters. You want to write Indonesian? Still great. There are a few other languages, some of the Aboriginal languages, I think. It's actually a nice trivia question. You can puzzle your tutor. Name languages which only use ASCII characters. So that's great. Alright, what about you want to do other languages? Well, there's a whole family of European languages and European derived languages, well, at least where the character set is European derived, that you can get by almost with ASCII. German, French, Spanish, Italian. A lot of you probably did one of those in school. You can write most German words, most French words, most Spanish, Italian, Swedish words with ASCII characters. There are a few you can't write in ASCII. Some of which gets used in names. You talk to, say, someone is Swedish and say ASCII's great, and they say, well, I can't actually spell my name with ASCII characters, and they get a bit grumpy about it. I guess they've got a point. Tagalog would be another one. Swahili, another, two very widely used languages. Almost ASCII. All right. So you can sort of get by in these languages, and there are weird extensions to ASCII that were developed for these, which thankfully we no longer need to worry about. Thankfully they're disappearing, which lets you do these languages by doing ASCII plus a little. Many other languages use a pile of characters, just none of which are in ASCII. You Thai, you get nowhere with ASCII. You want to write Arabic, sorry, Cyrillic, and so on. So what's the solution there? The solution, it's been around for a while, it's called Unicode. It specifies numbers for 40,000 characters. Well, this gives it coverage of pretty much all the world's languages. I think there are a few languages they're still working on that really aren't in use anymore, but that's Unicode. Unicode is great. Sorry, we're not going to do Unicode in this course. You go on to COMP1511, you can learn Unicode. Not a hard thing to learn about. Well, yes and no. What we teach you about it isn't hard. It has some interesting properties. It doesn't really affect what we have to learn in this course, which is why we don't cover it. And there's a nice thing is ASCII is actually a subset of Unicode. So everything you learn about ASCII will sort of carry on in a funny way into Unicode anyway. So that's the last we'll hear about Unicode in this course, but we will have to do a bit more about ASCII. Yeah, all right. 128 characters to integers. You don't have to remember these numbers. All right, so apparently little a is 97. You don't have to remember that ever. Also, don't put that in your program. Why not? Because C has embedded in its very syntax a way to get ASCII codes. If you put little quotes around a letter, that actually says to C, give me the ASCII code, the ASCII number for little a. So that's the same as happens to be the same as 97, which is the ASCII number for little a, and that's the same as putting 65, which happens to be the ASCII number for big A. And this would print out 32 and 10, which are the ASCII codes for space and new line. Alright, so don't ever put these numbers in your program. I think 115 style tries to spot that and warn you, because students, they get all excited. I know ASCII now, I can put 65 in my program and a big A will appear. Now it's nice you know that, it's great you know that. It's actually not a bad thing to do in a little experimental program, but once you've experimented with it, don't do it again. Don't put ASCII codes in your program. If you use single quotes, it just makes your program so much more readable.
One useful way of thinking about this is that you can think of the single quotes around a letter a lot like a hash define. So anytime where you'd want to use a hash define, the exact same thing, you'd want to use something that's more useful than just a random number. So you're going to use single quotes around that letter.
Alright, here's a little bit of code. I'm not going to run this code for you. I've got a program to run for you shortly. Pre-written. So it puts the ASCII code for little a into C1, the ASCII code for new line into C2. Alright, we want to put it out. So here's a new C library function. It actually comes out of stdio.h, like printf. And it does a really simple task. It just outputs a single byte, is what it does. So we can give it the ASCII code for little a, say output this byte, and a little a will appear on our screen if we're writing to a terminal. We can give it the ASCII code for a new line, and output will go to a new line. So these things here do the same as this, which does the same as that. And in fact, we could put a slash there. Oh, that should be a C1. That's the trouble. I hate putting non-executable code in lecture slides, because then you don't know whether it executes or not. So, all right, and this is what I've said. This does the same again. You could do that. That will print out as a on your terminal. This will print out as a new line on your terminal, but don't do that. And you see why. What you think? Looking at that, you're thinking, what the hell does that do? I can't remember. Unless you've got a tattoo of the ASCII code on your hand and look at it. But if I do see that, I can think, oh, puts out a little a. See this? Thinks, puts out a new line. Really readable, impossible to read. Lovely. All right. Oh, so yeah, printf new format %c. What does that mean? It really means output a byte, but we use it normally when we're outputting a character. So this creates a possibility for me. I could use a loop and see all ASCII characters on my screen, and I think I've got that ready to go. Oh, I do. Alright, look at my cunning plan here. Alright, so this is, again, this is sort of an experimental program designed to check out what's happening, explore the world of ASCII. I've cheated here. I know that 33 is the first printing ASCII character, and 126 is the last printing ASCII character. So I'm looping through all the printing ASCII characters. We can change it shortly and see the other ones if you want. But then I'm saying this ASCII number will be displays as this character. And I'll go through all 96 printing characters, is it? Was it 93? My counting's not very good. Let's try it out. DCC ASCII.c -o ASCII. And run it. And what do we get? And it's going through all the possible printing values in order. So the very first printing character, a 33 in ASCII, is the code given to exclamation mark. 34 to double quotes. 35 given to hash. Yeah, another weird trivia question. Ask your tutor, why is exclamation mark the first printable ASCII character? And we can keep going through it. You can see them here. And it goes through a pile of punctuation characters. Oh, here's an interesting thing. All the digits 0, 1, 2, 3, 4, 5, 6, 9 sit together in ASCII codes. So it doesn't go, here's the code for 0, 1, 2, 3, 4, and then here's the code for semicolon, or it doesn't put them in weird orders. They're consecutive. So they're consecutive and contiguous is what I'd say. They're one after another. And that's really useful when we're programming. It lets us do some tricks with that. Oh. What's happening here? There we go. Same applies. We've got then we get some more punctuation characters, less than, greater than, and so on, at, useful for email addresses. Then we get the capital letters, and they're all together again. So it goes capital A all the way through to capital Z's. Code number 65 all through the way through to number 90. Same applies to little a to little z. So we know if we get a code between 97 and 122 inclusive, it's a lowercase letter, and that's also useful. Makes our coding easier. I'll show you programs that use that. All right, let me modify this to show you the non-printing ones. We'll go through all 128 codes, but they're not very exciting seeing the non-printing ones, but just for you. We should see new line do a new line when we print it out. We run the program. Oh, yeah, 127 prints out weirdly, doesn't it? Huh. Alright. Oh, my terminal doesn't know what to make of the earlier ASCII codes. That's not a bad sign. You see something weird printing. Maybe I'm printing out a non-printing ASCII character. New line is here. So you can see new line printing out. Yeah, what are 11 and 12? You can research that. Alright. So they're the non-printing ones. So there are some numbers in that range that either do something like new line or something we don't know about. You can research that if you really want. That's not important. But it's a big thing for us that little a to little z are all together. Same for big A to big Z. And the same for the digits. They're all in sub-ranges. Makes some coding easy. Alright, so that's looking at those numbers. And yes, these are all the characters you'll get. So if you're working with ASCII, there's nothing else. If there's another character you want, it's not there. As I've said, this terminal, for example, supports Unicode. It's set up to write thousands and thousands of different characters. So that's a possibility, but we're not going to get into how you would do that or the implications in 1511. And apologies to those of you who are native Korean speakers, for example. You won't be able to write out Korean with your C programs. Where are we? Oh, so that's that program we just saw. So let's suppose in C I have an ASCII code. I've got a number 0 to 127. How do I know if C is a lowercase letter? I could do this test. I'd say does C have a code that's greater than or equal to the code for little a and less than or equal to the code for little z? If it is, it must be a lowercase letter, because we saw those codes were all together. So if it's in that range, it's a lowercase letter. How do we check if C is a digit? Same thing. Is its code greater than or equal to the code for whatever the code is for O. Notice I'm writing this. I don't embed in my program whatever the code is for O. What was the 0? Sorry, what is the code for 0? The ASCII code for a 0, writing up the digit 0, is a 48. The ASCII code to write out the digit 9 is 57. And where was little a? Little a was further down, was 97. So I don't put 97 here. I can just as equivalently say do that. And Tom said, yeah, I guess some students put 97 and then they think, oh, that should be a hash define, and they hash define ASCII code little a 97, but you don't need to do that. You've got single quotes. Oh, and here's a nice trick. So if I want to convert the ASCII code for a digit, so this is 48, this is 57. If I want to convert this ASCII code to a 0, I've got 48 and turn it into 0, 57 turn it into 9. What do? Subtract 48 from it, which is the code for little 0. So this, given the ASCII code for a digit, gives me its value as an integer, its corresponding integer. Yeah, nice trick. Classic programming trick. Oh. All right. Oh, I want to code this. This is just too frustrating. All right, bear with me. Oh, this is not too bad actually. We'll call this getChar test. There we go, getChar test.c. All right, save it to start with. Dump that comment because it's no longer true. Let me show you using the function getChar. I'll print out a message and then I'll say int c equals getChar. getChar reads a byte, and in this course that byte's going to contain an ASCII code. And if you're reading from a terminal, it's very likely to contain an ASCII code anyway. But alright, so let's try that out. Hopefully I got all of that right. Saved it, compile it. getChar, what do I call it? getChar test.c. Oh. That's sad. All right, away we go. Enter a character 5. I read 53. Let's try another one. What do we remember? Enter a character. Little a was 97, wasn't it? Yeah, there we go. So getChar is giving us back the ASCII code for characters. And if we want to see the character, we can just tell printf to output it as a byte. And away we go. I'll put in big A, what was that, 63? I can't remember. 65, which is big A. Oh, so there's getChar. Alright, Oh, I will show you one thing here. Yeah. So I say enter a character. And I type in a character. Nothing happens. Why is that? Well, that's not so obvious. What's happening is the terminal is not sending anything back to the program until a whole line of input is read. So until I hit an enter, it won't send back anything to the program. Program just wants to read a single character, but the terminal's not giving it anything until it's got a whole line. Why? It's sort of done for efficiency. The terminal doesn't want to be bothering the operating system sending stuff back to the program until it's got a lot of it. Is there a way to change it? Yeah, there's a complicated way to tell the operating system not to do this, but which we won't do. But just be aware that you'll have to supply a whole line of input. Even if you're just trying to read one character, nothing will get to your program until a whole line of input is sent. Let me show you something else. Let's read 2 characters and show you. Let's suppose we want to read 2 characters like this. Let's stop that program. So we'll enter character G. Oh. What happened there? I didn't get to enter another character. Let's put this message here. What's happening? I don't understand what's happening. Let's put another message to enter another character. Run this. This is sort of a common thing that afflicts when they start first starting using these functions. I'll type in a character. Well, we'll go with the % symbol this time. Yeah, things get weird. I read 37, which is %. Yeah, that makes sense. I read 10, which is nothing. Alright, so I typed actually 2 characters. I typed % and I typed the new line, and that's a character in its own right. So new line is a character. It's number 10. So the next thing we read is 10. So there's no way for me to then enter another character here. The weird thing you might see people do is this. Assume there's a new line coming and throw it away. Yeah, maybe I should be checking it's a new line, shouldn't I? Yeah. I can try that out. But just the big thing here is new line is a character. Let me recompile my program. Yeah, so that's sort of a weird trick to get around the fact that new line is a character, and I want to read character new line and then read another character and report what that is. Sort of weird. Alright, let's keep going on. There's a big thing now coming. This sort of stuff, you'll have bugs with this, but then you'll figure them out. We get to a more difficult concept. Oh, this slide really needs work. I thought maybe I got a better slide here. Yeah, sorry, these slides really do know. GetChar returns an int. If it's coming from a terminal, this int's going to be probably an ASCII code 0 to 127. If it can't read something, ignore the typo there, it returns a special value. The special value is almost always -1, but there's a hash defined for it called EOF. So getChar, two possibilities. Either it succeeds and it gives you back a value which will be 0 to 255, guaranteed, but in this course we're going to be reading things that are ASCII codes, so it'll be 0 to 127. Otherwise it sends you back a special value EOF. Yeah, sorry, that explanation is not very good. EOF stands for end of file, and that we don't do file I/O in this course. So, but it means, really what it means was nothing could be read. It's not a character. It's not an ASCII value. It's, as I said, it's actually really -1. It's an extra value. It's a special value. That leads us to have code like this, where we read until we can read nothing more. We don't need this until week 7. So in week 7 lab after the break. So it seems a long way away. So, but you will be doing code, using code like this in the week 7 lab. That says, give me a byte getChar, and then while you don't give me EOF, while you can print out I read this, and then get another byte. It's not the only way to write this loop, but using what we've seen so far, that's sort of the sensible way. So that loop keeps going until getChar returns this special value EOF to say, oh, I couldn't read any more bytes. And I think we've got that code there in there. So I've got it all ready to go, and we can try it out. And run it. Alright, so we can type in D and a new line, and they're saying D read, ASCII code 100, new line read, ASCII code is 10. Notice the weird way the new line prints out as quote, and then the quote, next quote on the next line. But we could try typing in 1, 2, 3, 4, 5, 6, sorry, 4, 5, 6, 7, 8, 9. Oh look, there we go. Or we could type in A, B, C, D, E, F. Oh. Alright, how do we tell the program that there's no more input? So it's possible if input were coming from, say, over a network, like a network connection, or coming from somewhere else, it would be finite. But input from a terminal is sort of infinite. I can keep typing forever. There's no limit. If it was coming from a file, maybe the file only contains 100 bytes and there's a limit. Alright, there is a way to simulate, a special way to simulate there's no more input available. On Unix-like systems, terminals are normally set up that if you type a special sequence, it means to the program no more input available. The special sequence is Control D, and that's a message to the operating system. The program doesn't see the control or the D. No character gets passed to the program. Instead, the operating system tells the program no more input available. And getChar, when there's no more input available, returns EOF. So I'm going to try that out. I'm going to type Control D. What happened there is the operating system said, oh, Android doesn't want to give any more input. getChar was then told no more input available, and it in turn returned to the program, oh, -1, EOF. Sorry, I can't give you another byte. My loop exited, program exited, everything over. So that's a classic programming pattern that does something for every character in a program. So that's, you saying, do I have to memorize that? No, not really. We'll give you. You'll go back. I think the week 7 lab exercise will say actually use this code as a starting point, and you'll do things with every. In fact, I think week 7 lab. I think you'll get to do some encryption, going back to the sort of genesis of modern computing with code breaking in World War II and Alan Turing and friends at Bletchley Park. You'll get to do a little encryption and decryption in the week 7 lab exercises, and you'll use a loop like this to read the characters you're encrypting and decrypting. All right. Let's flip back to where we're up to. Oh, just for comparison, if we wanted to read numbers until no more numbers were available, we could do that loop with scanf. So that's sort of the same loop with scanf. We've seen already scanf returns how many things it's successfully read. And almost always we're asking for just one thing. It is possible to ask for 2, 3, 10 things, but it's better to keep things simple with scanf. And so we've asked for one integer. If we got one integer, then we print out this and go around again. So that's the equivalent sort of loop that would read integers until there was no more integers. One possibility, by the way, would be you type something that wasn't an integer. That loop would then stop. All right. Here's putting together two things we've looked at in the previous code. I wanted to convert characters from little letters to big letters, from lowercase to uppercase. This is my code to do that. So I've got a function. It's given. In is ASCII byte code. Out, ASCII byte code. If in is the ASCII byte code for a lowercase letter, out is the corresponding uppercase letter. If in is little j, say, out will be the ASCII code for big J. And I don't know what either of those are. How would I make this work? It's a nice design problem because it's saying, well, what do you do if you're given a letter outside that range? Just return it unchanged is my design decision, and that makes it a really nice function actually. So rather than having an error if you're given something that's not a lowercase error letter, this just returns it unchanged. It makes it quite a useful function. That's a nice design decision. If it is a lowercase letter, we work out where it is in the alphabet. So this will give us a number 0 to 25. If character contains the ASCII code for little z, the result will be 25. If it's the character code for little a, the result will be 0. So this will give us a number between 0 to 25. Yeah, there really should be a comment there saying that, shouldn't there? That would be smart. This then gets that value and adds it to the ASCII code for big A. Now I don't need to know that that's 65 and that's, was it 97? I can just put the values there and all of this logically works. Oh, do I have a program for this? I do think I have a program for this, which I'm going to go to. I think I've put it all together. Uppercase, there we go. Uppercase. So that's the code we've just talked about. Yeah, poorly commented, Andrew. It should say, yeah, that's 0 to 25. So there's my function. And here is me using it. So this is the same loop we talked about. Reads characters until there are no more characters. If I get a character, I make it into uppercase and then I output it. Oh, that's quite nice. What was it called? It was called uppercase. Alright, let's try it out. Will it turn this to uppercase? Oh, look at that. Right, let's try out some more text in it. Let's put a potential email or message in there. Oh, well, that didn't go well. Let me start again. There we go. Ah, perfect. Gets right. Look at that. Working perfectly. Converting lowercase to every lowercase letter to uppercase. Now, if we put other characters in there, or a few numbers, I'll go through unchanged. So that relies on 0 to 9 occupying consecutive contiguous positions in the ASCII codes and delay to little z. That's beautiful. Alright, often for code like this you should be thinking, I'm setting, so I've done this is a learning lesson. Every new programmer should write code like this. But in general, when we get to be working professionally, before you launch into writing a task like this, you should ask yourself, is this code that other people would need? Is this code that, you know, someone might have already written code, debugged code, been tested by tens, hundreds of thousands of people? If the answer is yes, then you should look around for maybe existing code that does what you want. So in this case, there's a set of C functions in ctype.h, and one is toUpper that does exactly this. So in general, you'd be smarter to use toUpper from ctype.h. Alright, where am I at? Alright, we just saw that. Oh, alright, yeah, so there's a set of useful functions you can get by hash including c.h. If C is an ASCII code of an uppercase letter, sorry, you can make it lowercase, you can make it uppercase, uppercase, lowercase. You can check if it's a letter, check if it's a digit, check if it's a lowercase letter, check if it's an uppercase. Nice functions in ctype.h. I guess I'll talk about this briefly, and this is not a bad point. We're going to come back. So there's another type which we can get to talk about in our next lecture. There's a new numeric type called char, which stores small integers. So we'll open the next lecture talking about this. How small, you say? How small an integer can it hold? Well, what you can really depend on is it can hold the values 0 to 127, and that's not a lot. That's not very big. You're saying, yeah. What it can always hold is it can always store ASCII character codes, and that's generally what it's used for. So it's actually just a normal integer type, but what it mostly gets used for is storing ASCII codes. And that's the only thing you should use it for in COMP1511 is storing ASCII codes. It's even, you use it even less, arrays of ASCII codes. The only place you should use it in COMP1511 is arrays of ASCII codes. So it's a normal integer type, But so you could do this. You could say, have a char variable I, j, k, and do arithmetic in them. That all works because the numbers we're using are really small, really small. But even if you're doing arithmetic that's really small, you're writing a loop that goes 0 to 9, don't use char. Don't do that. If it holds regular numbers, just use an int type. Only use char in this course when you have to hold arrays of character codes. Saying, why would I want arrays of character codes? For that, you will have to wait until next week. Sorry, not until next week, until Thursday. 2 days time, not so bad. 2 o'clock Thursday, we'll be back to dealing with arrays of character codes in various interesting ways. It's a good point to stop, unless Tom has some questions or comments or things I've forgotten to say. I'm signing out for today.
Don't think I do.
All right. Thank you very much for Luca in the chat. Busy fielding questions I see in the chat. Thank you to Tom for your help. And yes, everyone, please stay warm, dry, COVID safe, and I'll talk to you on Thursday.